Guys, welcome back to TechDose, and in this video we will look at minimum difference in sums after removal of elements, which is from Leetcode number 2163. Let's now look at the problem statement. In this problem you are given a zero indexed integer array nums consisting of 3 n elements. You are allowed to remove any subsequence of elements of size exactly n from nums. The remaining 2 n elements will be divided into 2 equal parts. The first n elements belonging to the first part and their sum will be called sum first. The next n elements belonging to the second part and their sum will be called as sum second. The difference in the sum of the two parts is denoted by sum first minus sum second. For example, if sum first is 3 and sum second is 2, then their difference will be 3 minus 2, which is 1. Similarly, if sum first is 2 and sum second is 3, then their difference will be minus 1. We need to return the minimum difference possible between the sum of the two parts after the removal of n elements. Now, according to the problem, the number of elements in an array will always be a multiple of 3. So that has to be noted. And if you look at this array here, which is nums, if I say that the number of elements are 3 here, then within these elements I have to remove n by 3 elements first of all. And then from the rest of the elements I have to take the first n by 3 elements into the first array and the last n by 3 elements into the second array. So here if I decided that let's remove 3. So if you remove 3, then you will be left with 1, 2. So the first half will be in the sum left and the second half will be in the sum right. So if you take the difference, then it is going to be minus 1. So this is one option. Another option could have been you could have removed this 1 instead of removing this 3, and so the array would have been 3, 2. In this case, the first half will give you sum 3, second half will give you sum 2, and if you take the difference 3 minus 2, it will be 1. And the third case would have been to just remove 2, and in such case your difference from the first half and second half sum will be 2. Out of all these options, minus 1 is the smallest, and that is why it is the answer, right? If you look at the second example, in the second example we have n equals to 6. That means we have to remove n by 3 elements, which means 2 elements, and we can choose any 2 elements to be removed. So if you try the brute force approach, then each element will have 2 options of either you can remove it or you can retain it, isn't it? And out of these n elements you can only remove n by 3 elements. So you can say that approximately you can have 2 to the power n by 3 possibilities, or you can just say that it will be order of 2 to the power of n, right, which is a very large number. If you look at the value of n, it is 10 to the power of 5. Okay, so 2 to the power n is not a feasible solution here. So you can make out that recursion and simple DFS is not going to work. Okay, now in this particular case, let's assume that you had removed this 9 and 8. If you had removed 9 and 8, then your array will be 7, 5, 1, 3. So in the first half you will have sum as 12, in the second half you have sum as 4, and the difference will be 8. So this is one possible way to remove n by 3 elements and get the left sum and right sum, and the difference is 8. We need to minimize this difference, and if you try to minimize it, then it will come as 1 as explained in this problem, right? So that you retain 7 and 5 on the left side and 8 and 3 on the right side. So you remove 9 and 1. So in such case your difference value is going to be 12 minus 11, which is 1. Okay. So if you look at the constraint, the number of items will always be a multiple of 3 and n value is less than equals to 10 to the power of 5. Looking at this, since you know that I need to solve it within 1 second, I need to have computations less than 10 to the power of 8. So in the worst case, you can go for n log n algorithm or something better than n log n. Okay, but we should not try to go beyond n log n. Looking at the constraint, you can make it out. And each of the element has max value of 10 to the power of 5, right? So I hope it is clear. Let's now look at some observations. Now in this case, if I assume that n is the number of array elements, okay, I have already taken an example where n is equals to 6. So what we need to do is we need to remove n by 3 elements. Okay, 1/3 of the elements have to be removed, and from the resulting array we will be getting the left sum and right sum, and our goal will be to minimize the left sum minus right sum. If I want to minimize left sum minus right sum, then I need to minimize the value of sum left and we need to maximize the value of sum right. That should be done. Okay. Now, given this example array, if I try to remove this index 1 element and the index 5 element, then I will be getting the array 2, 1, 8, 5. And if I take the left sum, it will be 3, the right sum will be 13. And if I take the difference, then that is going to be minus 10. And this will be the minimum possible sum left minus sum right. Okay, so this is the optimal decision which I have already shown you. In this case, if you observe, if I ask you about what elements can you actually have in the left array, that means in the left partition. So you can never have this 4 and 5 in the left partition, because how can you have it? Like, even if you had removed this 3 and 1, you will end up with 2 and 8, because the problem constraint says that whenever you remove n by 3 elements, whatever array you are left with, you have to take half of the elements on left side and half of the elements on the right side. So if this is the constraint, then you know that the last n by 3 elements can never come in the left hand side array. And for the same reason, the first n by 3 elements can never come on the right hand side array, right? It can never come. So we know that if I have to find sum left, then the options will come from 0, that means index 0, to less than 2n by 3, where this 4 is actually 2n by 3, because we know that n is equals to 6, right? So 2n by 3 will be 4. So the elements that can actually be included in sum L in the best case, or you can say in the worst case, or whatever case, can only be included from 0 to less than 2n by 3 index, right? But not including 2n by 3. And for the same reason, the elements that can be included in sum R in the worst case can range from n by 3 to less than n, where n is equals to 6, right? So less than n by 3, which is this 2, to less than n. That means from index 2 to index 5, elements can come in the right hand side array. And how it can come? If I remove, let's say, this 5 and 4, then 2 and 3 came into the right hand side array, right? Okay, so this is an important observation. Elements in the left array can only be included from 0, inclusive of 0, to 2n by 3, excluding 2n by 3. And the elements in the right array can only be included from 2n by 3, including this, and excluding n. So I hope this is clear. Once it is clear, then we have to define an optimal partition point. What do you mean by optimal partition point? Here, the partition point is between 1 and 8, or you can say that the partition point is at 1, not at index 1, but at this value 1. Okay, so if I had taken a partition here, then I will say that this will be the left array and this will be the right array. It could have been anywhere. It may not be in the middle. The partition point will range from index 1 to index 4, you can say. I mean, you can say 3, right? Because I am putting the partition to the right hand side of the index. So the partition point can be put at any place 1, 2 or 3, but it cannot be placed at 4, 5 or 0, because you need at least n by 3 elements on the left side and n by 3 elements on the right side, even after removing the elements. Okay. Let's say that the partition point was put here at index 2. This means at 2 to the right hand side of index 2. Then you have 3 elements on the left, 3 elements on the right, but you just want 2 elements on the left and 2 elements on the right. So you will optimally remove one element from the left hand side. Okay, and I want to minimize the sum on the left hand side. So which element will you remove? You will remove the maximum element, right? And on the right hand side, you want to maximize the sum to the right hand side. So if you want to do that, then which element will you remove? The minimum one, which is 4, isn't it? So if you put a partition point at index 2, then you will end up with 2, 1 on the left side and 8, 5 on the right side. This is how you decide that for a partition point, what will be the sum on the left side and what will be the sum on the right side. But this partition point may not be the optimal partition point. Maybe putting a partition point at index 3 would have been optimal, right? So if you put up a partition point at index 3, then you have 4 elements on the left side and 2 elements on the right side. In this case, if you have 4 elements on the left side, you need only 2 elements, so 2 elements have to be removed. And since you want to minimize the sum on the left hand side, therefore I will be removing the maximum 2 elements. That means 8 will be removed and 3 will be removed. So I will end up with 2 comma 1 on the left side, and on the right hand side you have only 2 elements and you needed only 2 elements, and by 3 elements, right? So you cannot remove anything. And once you are done, then the left sum is going to be 3, right sum is going to be 9, and this is going to be minus 6, right? Now if you compare with the previous case, then the answer here was 3 minus 13, which is minus 10. Here it is minus 6. So minus 10 is a better result. And again you will be trying with the another partition point which was at index 1, which we didn't try. Okay, so if you try that out, then again you will find that you have 2 3 on the left side, only 2 elements. You wanted 2 elements, so you cannot do any removal. On the right hand side there are 4 elements, so you can do 2 removals. And which 2 elements will you remove? You want to maximize, so you will be removing the minimum element. So 1 and 4 will be removed. So you will end up with 2 3 on the left side and 8 comma 5 on the right side. So this is going to give you 5, and this will give you 13. So 5 minus 13 is going to be minus 8. So out of all these options, minus 10 is the best option. So if you look at the run for the partition point, it is running from index n by 3 to less than 2n by 3. Okay, so that means the partition point also have exactly n options, or you can say n by 3 options in this case, right? The partition point have exactly n by 3 options, from n by 3 and including n by 3 to 2n by 3 and not including 2n by 3. I hope this is clear. Our goal should be to find the optimal partition point out of all the available n by 3 options which are available. So in this case, if I take an array of size 9 from A to I, if let's say I have put a partition point between E and F, which means that I am putting a partition point at E, then there are 5 elements on the left side, n value being 9, n by 3 value will be 3, and there are 5 elements on the left side, so I have to remove 2 elements. So I will be removing the maximum 2 elements. And how do you track the maximum 2 elements in any pool? You can take a max heap for this, right, which will be optimal. And similarly, on the right hand side you have 4 elements and you just want n by 3, which is 3 elements. So since I want to maximize the sum on R, that means we want to maximize the right hand side sum, so I will be removing the extra elements, and that has to be the minimum elements. So for this you can take min heap to track these elements out, right? So in this way, if let's say B and D were the maximum elements on the left side, you will end up with A, C, E on the left side, and on the right side if H was the minimum element, then this will be removed and F, G, I will be taken. So A plus C plus E minus F plus G plus I will be calculated, and that is how we can get an optimal minimized value for this particular partition point. But we will not just be doing for this partition point, right? The partition point will range from n by 3 index to 2n by 3, but not including 2n by 3 and including n by 3, right? We have to try all the possible partition point. So if we assume that we remove k elements from the left side, then n by 3 minus k elements will be removed from the right side, so that overall we end up removing k plus n by 3 minus k, which is n by 3 elements, because we have to remove exactly n by 3 elements. So remove the maximum k elements from the left array, and you know how many to remove because you know what is n by 3 count and how many elements are there on the left side. So if you take the difference, you will know how many elements to remove from the left side. So remove the maximum k elements from the left side because you want to minimize the left sum, and simply remove the minimum n by 3 minus k elements from the right side because you want to maximize the sum on the right hand side. Okay, so I think the goal is clear that we will be trying all possible partition point to find the optimal partition point to minimize the sum on the left minus sum on the right. Okay, and I have already shown you the calculation for each of the partition point. So if you try to move from one side to the other, then simply you can take it in the form of a heap. Like let's say if I take this partition point where I say that the partition point at index 2 has to be calculated, on the left hand side I will be maintaining a max heap. So let's say the max heap will be having 3 to 1, and on the right side I will be maintaining it in a min heap. So the min heap will be having 4, 5, 8. And out of these two, I know that I have to include only n by 3 elements on the left. So that means I need to remove one element. Which element to be removed? 3 will be removed. So the sum here will be 2 plus 1, which is 3. And on the right side, we need to maximize the sum. So I remove the top of the heap, which is 4. And that will be 4 plus 8, which will be 13, right? And if I take the difference 3 minus 13, it is going to be minus 10. And this has to be repeated for all the possible partition points, right? So I will be using the two-heap method, which is max heap and min heap. Max heap on the left side and min heap on the right side. But is this enough? Now, if you think about the actual goal of the problem, then we need to move the partition point from n by 3 to less than 2n by 3. And we have to always track the maximum sum that you can get on the right hand side. So if we can pre-compute the maximum sum on the right hand side starting at any index, like what if I say that after this index 2, like starting from index 3 till the end, the maximum sum is going to be 13. And what if I tell you that starting from index 4 to index 5, the maximum sum is going to be 9, which is 5 plus 4. So if I have pre-computed this, then moving from left to right, I can easily pick the minimum n by 3 elements, and I will also know that given a partition point, I don't have to calculate what is the maximum sum on the right hand side because it is pre-computed, so I can just look up and answer it quickly. Okay, so that will be a quicker method instead of for every partition point you go to right hand side, left hand side and start computing them. Okay, so what do I mean to say is, if you can compute a right sum array, like let's say right sum, the maximum right sum array, okay, which will tell you about what will be the maximum sum when you have actually included exactly n by 3 items. So if you move from right to left, if you just have the first item, have you included n by 3 items? N by 3 is equals to 2 here, right? So have you included 2 items? No, so let it be 0. But if you include 5, then yes, the sum will be 9. And if you include 8, then you have more than n by 3 elements. So whatever amount you are overflowing with, that means we have 3 elements, I just want 2 elements. So I will be removing 1 element. So remove it using the min heap, and you will be removing 4, so the sum is going to be 13. And do this for all the items, right? So for index 2, if I can maintain from index 2 to index 5, what will be the maximum? You push 1 into the min heap, and out of all these 4 options, remove 2 options. So the 2 options are going to be 4 and 1, and here also the maximum is going to be 13. This 13 here means that if you had put a partition point at index 1, and if I ask you that what will be the maximum sum on the right hand side starting from index 2, it will be 13. Okay, and do I need to do for this 1 and 0? I don't need to do for them, because I know that the right hand side elements will not go beyond this n by 3 index. That is not possible. Okay, so I can keep it as zeros. So this will be my pre-processing. But how to do this pre-processing? If you think, then what I can do is, I can just take a maximum right sum array of size n, and I will pre-initialize all the values with 0. Let's pre-initialize all the values with 0, and I can take a min heap. Simply take a min heap, okay? And now go element by element from right side. That means from index n minus 1 to index n by 3. To index n by 3. We will be moving, and we will be pushing the first element into the heap. So 4 will be pushed into the min heap. Okay, and I will be maintaining the right sum. The right sum value starting from 0, 4 will be added, it becomes 4. Now I will check if the min heap size is equals to n by 3, the n by 3 size. Then only I will be updating the sum. So min heap size is only 1, n by 3 size is 2, because I should have at least sufficient elements on the right hand side array to make it valid. One element will not be valid, so I will be skipping this. Okay, 5 is coming. 5 will be pushed into the heap, and 5 will be updated in the right sum. 5 plus 4 is 9. Now check the size. Size is n by 3, which means that this is a valid array, and I can update this sum to 9. Okay, and move to the left hand side. When you have 8, you add 8 into the min heap, update the sum, it will be 17. Now you have to check, every time you have to check that this size of the heap is actually greater than n by 3. So you need to remove one element to make it equals to n by 3. Which element will you remove? 4. So 4 will be removed from here. Okay. When 4 is removed, 4 sum will be subtracted from the right sum and this will become 13. And now you update this sum to 13. Go to the left hand side, which is 1. So add 1 and update the sum from 13 to 14. Okay. Now find the size of the min heap. It is 3, which is greater than n by 3. So this means I have to remove one element. So remove this one, top of the min heap, and update the sum. It will become 13. And again write 13 here. And we are done. We are done doing the pre-processing. Now once we are done pre-computing the maximum possible right sum available from index n by 3 to n minus 1, after this we have to take a partition point starting from index n by 3 minus 1, which is this index 1, and going all the way to less than 2n by 3. Less than 2n by 3. So 2n by 3 is this 4. So less than this is 3. So I have to try for all the possible partition point 1, 2 and 3. So what I will do is I will be moving from index 0 itself. Okay. We will be moving from index 0, and let me just clean it up because we are done with the pre-processing. I don't need the min heap anymore. Okay. What I need now is a max heap. Why I need a max heap? Because I need to minimize the left array sum. So I'll be taking a max heap to pick the maximum items and just remove them. Right? So let's do it. When we are at index 0, we will be adding 2 in the max heap, and I will be maintaining the left sum, which will be equals to 0, and this 2 is added, so it will be 2. Find out the size of the heap. Size of the heap should be n by 3. Otherwise it is invalid. So it is invalid currently. So this is not a valid partition point. Go to the next item 3. 3 will be added in the max heap. 3 will be updated in the sum. Find out the size. Size is equals to n by 3. So yes, it is valid. And if it is valid, then you know that in the left sum you have 5. What will be the right sum? You want to minimize the left sum, and that is equals to 5. You want to maximize the right sum, and that you can find from this pre-processed array at index 2. At index 2 you have 13. So that means I want to minimize the difference. So min diff value will be, let's say, infinity. And now it is going to be 5 minus 13, which is going to be minus 8. So update it to minus 8. Okay, we will be trying to minimize it. And now you proceed further. You are seeing 1. So 1 will be added into the max heap. Okay, the sum is updated to 6. Now the number of elements in the max heap is greater than n by 3. So I need to remove one element. And since I want to minimize the sum, I will be removing the max element, top of the heap. 3 is removed. So the sum will be updated from 6 to 3. And now at this point, when the partition point is put at index 2, look at index 3 item, and this is saying max sum on the right side will be 13. So 3 minus 13 is minus 10. Minus 10 is less than minus 8. So update this to minus 10. And now what happens is you move the partition point to this index 3. Okay, so when you move to this index 3, then this 8 will be added into the heap, into the max heap, and 8 will be updated in the sum. This becomes 11. And now the number of elements are greater than n by 3. So you remove the max heap top element, and you are left with only 2, 1. So here the sum will be updated, and this becomes 3. Okay. Now the left sum is 3. The right sum will be equals to, look at index 4, and it is saying that the max sum on the right is 9. So 3 minus 9 is minus 6. But minus 10 is lower. So don't update it. And we are done. We have to stop at this index, which is less than 2n by 3. Okay. So after tracking this entirely, you got minus 10 as the minimum sum difference between the left hand side and the right hand side by trying out all the possible partition point using max heap on the left and min heap on the right. So this is the two heap method by doing pre-processing, and in this case the pre-processing step would take n log n time because we are looking at 2n by 3 elements and pushing and popping all of those elements, right? So since 2 is a constant, I will be taking n log n, and after that we are again moving from left to right and pushing and popping 2n by 3 elements. Again I will be taking n log n time. So both the time complexities combined together will be order of n log n, and the space complexity here will be equals to the min heap will be storing approximately n by 3 elements, because when the elements increase to n by 3 plus 1 we will be removing one element, and the same goes for the max heap as well. So I will say n by 3 as order of n. So space complexity is order of n also because of this the right sum array, which will be tracking starting from any partition point or any index what is the maximum sum you can see on the right hand side. So that will be order of n. So this is the time and space complexity. I hope it is clear. Let's now look at the code. If you are someone who is looking to prepare for top product based company within a limited time of just 3 months, then we have brought for you both the DSA and the system design live interview training program. The most important feature of this program is you get a filtered and condensed structured curriculum, in-depth discussion of all the topics, and my guarantee of your understanding, one-on-one guidance with me, and live weekend classes. To know more about the training, you can WhatsApp us on this given number. In this problem, since we were given 10 to the power 5 number of elements and each of the elements can be 10 to the power of 5, so the maximum number can be 10 to the power 10. So just to maintain that we don't go out of bound in terms of 32-bit integer, we have to take long integer. Okay. Now the nums array was given and I will be finding the number of elements, and simply step number 1 was to pre-process and build the right max sum from index n by 3 to less than n. Right. So we have taken a min heap because I want to maximize the sum on the right side, and initialize all the values to 0, which is the right max sum array, and iterate for all the elements from right to left. Whenever you see the element, push it into the heap, update the right sum. But if the heap size goes beyond n by 3, then we need to remove the top of the heap and also adjust the right sum. Okay. Once that is done, if the heap size is exactly n by 3, then that means it will form a valid right array, and so you can update the right max sum at I. Okay. So this was step number 1, the pre-processing step. After doing the pre-processing, in step number 2, we will be moving from left to right from index 0 to less than 2n by 3. Okay, and we will be maintaining the left sum, the min diff with the long maximum, okay, which is infinity in the 64-bit integer, and the max heap. Because I want to minimize the sum on the left side, I will be iterating for all the elements. Again repeat the same process, see an element and push it into the max heap, update the left sum. If the size grows beyond n by 3, remove the top of the heap and update the left sum. And if the size is equivalent to n by 3, then you update the min diff by taking the minimum of already known min difference, comma, left sum minus the maximum right sum just to the right hand side of the partition point I. Okay, where the left array will be from 0 to I, right array will start from I plus 1 to the last index. Okay. So finally we will be turning the minimum difference. I hope this entire technique is clear. If you still have any doubt, then feel free to comment below and I'll try to help you as soon as possible. See you guys in the next video. Thank you.